In this video, we are going to learn about the classification of real numbers. Now, the first sort of real numbers is the natural number. Now, we denote the set of all natural numbers using this notation over here. That is, we use the letter n to represent the set of all natural numbers. Now, what is a natural number? Now, the natural numbers are the numbers that we use for counting. Now, the natural numbers start from the number 1. And we can obtain the other natural numbers by successively adding 1. So we have 1 plus 1, that's 2. Then we have 2 plus 1, that's 3. 3 plus 1 is 4. 4 plus 1 is 5, and so on. This set keeps on going on forever. So if we use set notation, the natural numbers, the set of natural numbers is this set. Now, if we have a look at all of the numbers, we can see that each of the numbers are whole positive numbers. There are no negative numbers in this set, there are no fractions, and there are also no decimals. Now, the smallest natural number is 1. And there is no largest natural number because the set goes on forever. And we also call the set of natural numbers the set of counting numbers because we use these numbers to count. For example, I might say that I have 1 apple, or I might say that there are 2 cats in the room, or I can say that I have 3 oranges, or maybe I can say that there are 4 pens, or maybe I can say that I have 5 boxes. So in this way, we can use the natural numbers to count objects that we see in real life. So we call the natural numbers the set of counting numbers. Now we can move on to the next type of real number. Now the next type of real number is the whole number. And we represent the set of whole numbers using this notation over here. That is, we use the set W to represent the set of whole numbers. Now, what are the whole numbers? The whole numbers will include all of the natural numbers and the number 0. So all of the natural numbers, so we have 1, 2, 3, 4, 5, and so on. And along with all of these natural numbers, we have one more number, and that is 0. So this is the set of whole numbers. We start from 0 and we increase by 1, and this set goes on forever. Now, similar to the natural numbers, we can see that there are no decimals or fractions in this set. And in this set, all of the numbers are non-negative. 1, 2, 3, 4, 5, and so on, they are all positive, and we have the number 0. So we end up with non-negative numbers. And if we have a look at this set, we can see that 0 is the smallest whole number. And there is no largest whole number because this set goes on forever. Now we can move on to the next type of real number, and that is the integer. So we have the set of integers. And we represent this set using this notation over here. That is, we use the letter Z. Now, what are the integers? Now, in the set of integers, we have the number 0. We have all of the natural numbers, so we have 1, 2, 3, and so on. And we also have all of the opposites of the natural numbers. So we have the numbers 1, 2, and 3. So we will also have all of their opposites. That is, we will have the opposite of 1, which is -1. We will have the opposite of 2, which is -2. We will have the opposite of 3, which is -3. Similarly, we will have the opposites of all of the other natural numbers. So this is the set of integers. So in the set of integers, we can see that we have all of the numbers which have no decimal or fractional part. These are all of the real numbers with no decimal or fractional part. That is the set of integers. And if we have a look at this set, we can see that there is no smallest integer because this set goes on forever on the left, and there is also no largest integer because the set goes on forever on the right. Now we can move on to the next type of real number, and that is the rational number. Now we denote the set of all rational numbers using this notation over here. That is, we use the letter Q to represent the set of all rational numbers. Now, what is a rational number? Simply put, it is any number which we can write as a fraction. So that means that Q will have all of the numbers x, such that x can be written as P by Q, where P and Q are integers. And we also need Q to not be equal to 0 because we cannot divide by 0. So if we want to write P by Q, obviously the denominator cannot be 0. So Q needs to be non-zero so that P by Q is a defined real number. And other than that, if we have any integer for P and Q, then we will have a rational number. So this is the set of rational numbers. So we have fractions. All of the rational numbers are fractions. Now let us consider a few examples. First of all, let us consider the number 1 divided by 2. Now this is a rational number. Now the reason for this is that we have expressed this in the form P divided by Q. Here we have the number 1, that is P, and in the denominator we have the number 2, that is Q. So 1 by 2 is simply equal to P divided by Q, where P is an integer 1 and Q is a non-zero integer 2. So half will be a rational number. Similarly, if we consider 4 divided by 25, this will also be a rational number. And that is because P is 4 and Q is 25. Consider a number like minus 4 divided by 7. This is also a rational number. We can write this as negative 4 divided by 7. And here, P will be the integer negative 4, while Q will be the integer 7. So negative 4 by 7 is also a rational number. Now note that all integers are rational numbers. We can see this by using an example. Now let us consider negative 3. That is an integer. Now we can express this in the form of P divided by Q by writing this as negative 3 divided by 1. So here we can see that P is the number negative 3, while Q is the number 1, and that is a non-zero integer. So we have expressed the integer negative 3 in the form of P by Q, and so this will be a rational number. So all integers are actually rational numbers. Now, all rational numbers can be expressed as decimal numbers. Now, rational numbers will either have a terminating decimal expansion or a non-terminating repeating decimal expansion. Now, let us consider a few examples in which the decimal expansion is terminating. Let us consider the number half. This is a rational number, and the decimal expansion is 0.5. So we can see that there is only one digit after the decimal point. So this is a terminating decimal expansion. We can consider 4 by 5. That is another rational number. And if we consider the decimal expansion, that will be 0.8. Another example is 11 divided by 8. The decimal expansion of this is 1.375. There are only 3 digits after the decimal point, so we can see that this is a terminating decimal expansion. Now we also have some rational numbers with non-terminating repeating decimal expansions. For example, if we consider the number 1 divided by 3. If we consider the decimal expansion, it will be 0.333, and this will keep on going on forever. So we write that like this, with a bar over the 3 to indicate that it repeats forever. Another example is 2 divided by 11. Now the decimal expansion for that is 0.181818, and that pattern continues on forever. So we have 0.18, and we write a bar over the 18 to represent the fact that it keeps on repeating forever. Now we can consider another example, 19 divided by 18. If we consider the decimal expansion for this number, we will get 1.0555, and this continues on forever. So we write that as 1.05 with a bar on top of the 5 to represent the fact that the number 5, that the digit 5, keeps on repeating forever. So these are all examples of rational numbers with non-terminating repeating decimal expansions. Now let us move on to the next type of real number. Now the next type is the irrational number. Now irrational numbers are all of the real numbers which are not rational. That is, these are all of the numbers which we cannot express as fractions. For example, the square root of 2. No matter what we do, we can never represent the square root of 2 as a fraction, and so root over 2 is an irrational number. Similarly, root 3, root 5, and the square root of any number which is not a perfect square. We also have another well-known irrational number, which is pi. So these are all examples of irrational numbers. Now, irrational numbers can also be expressed as decimals. Now, every irrational number has a non-terminating, non-repeating decimal expansion. For example, if we consider the number square root over 2, the decimal expansion is 1.41421356,237, and this just keeps on continuing. And if we have a look at this decimal expansion, we can see that it does not terminate because it goes on forever, and it does not repeat. If we have a look at these digits after the decimal point, we can see that there is no repeating block of digits. So this is a non-terminating, non-repeating decimal expansion for the irrational number square root over 2. Now, let us consider a diagram to see what we have learned today. So first of all, we have the set of real numbers. Now this set can be split into two parts. The first part is the set of rational numbers, and the other part is the set of irrational numbers. Now in that set of rational numbers, we have the set of integers. This is because all integers are rational numbers. Within the set of integers, we have the set of whole numbers. This is because all of the whole numbers are integers. And within that set of whole numbers, we have the set of natural numbers. This is because all natural numbers are whole numbers. So this diagram represents the classification of all real numbers. Now let us consider a few practice problems. Let us try to classify all of the given numbers. Now consider this first real number, -3/7. Now this is written as a fraction. We can consider it to be -3 divided by 7. So that means we can write it as a quotient of integers, and so this is a rational number. Let us consider the next one. We have 5.34, and there is a bar on top of 34. So that means this is 5.343434, and that continues on forever. So that means this is a non-terminating but repeating decimal number, and numbers like that are rational. So this number also belongs to the set Q. Let us consider the next one. We have -8. Now, -8 is an integer. This is the opposite of a natural number, so it is an integer. So this belongs to the set Z. And since all integers are rational numbers, this also belongs to the set Q, and so -8 is both an integer and a rational number. Next, consider 0. Now, 0 is a whole number because the set of whole numbers has the numbers 0, 1, 2, 3, and so on. Now, all whole numbers are integers, so 0 is also an integer, and all integers are rational numbers, so 0 is also a rational number. Next, we have square root over 23. Now, 23 is not a perfect square, so that means that the square root over 23 will be an irrational number. And if we consider square root over 36, 36 is a perfect square, and because of that, the square root of 36 is 6, and 6 is a natural number. So that means that the square root of 36 is a natural number. All natural numbers are whole numbers, so this is also a whole number. All whole numbers are integers, so this is also an integer. And all integers are rational numbers, so this will also be a rational number. So root over 36 is a natural number, it's a whole number, it's an integer, and it is also a rational number. Thanks for watching this video. I hope you enjoyed it. Don't forget to comment, like, and subscribe. See you next time.